Hello, stats friends. We did it. We're in the last chapter, if you can believe it. So, chapter 12, it's going to start off with the chi-squares statistic and calculating for the goodness of fit. And then we're going to talk a little bit more about that in 12.2. And then for 12.3, we're going to go back and revisit our idea of linear regression, which will be a neat review getting ready for the AP exam. All right, let's talk about chi-square. So, what we're going to see today is we're going to go back to categorical data. So we're going to be working with proportions, but it's going to be a little more complicated in a sense where it's not just like a single, you know, variable outcome that we're looking at, or category, I should say. It's not going to be like a yes or no. Does it fit or does it not fit? It's going to be multiple categories. So I like this example because you know me and food, we get along. They're going to talk to you about the M&M's company and the proportion at which the colors are supposed to show up in, a bag of M&Ms. Because according to the factory, these are the percentages, which I think is fascinating. Maybe you don't. All right, so we're talking about an experiment, not experiment, I shouldn't say that, but a little activity that we could do in class, but we are winding down in time, so we're probably not going to do this activity live. However, we could always eat M&Ms while we talk about it. Jerome's class wondered if the distribution of color in a large bag of M&Ms differed from the claim that the company was making. So what they did is they took a random sample of 60 candies from a bag, and then here's what we're going to call their observed data, and we're going to somehow compare that to what we expected. So we're going to create a hypothesis test, essentially, a chi-square test, and we're going to have null and alternative hypotheses again. But I think, you know, there's a way to simplify how we do the hypotheses for this chapter. And I think we're going to use words instead of symbols, and that's going to help a lot. So the distribution of color in a large bag of M&Ms is the same as the claim distribution from the company. So that's going to be our null hypothesis, where it is exactly what the company said. And our alternative hypothesis is just going to state that it's not the same as the distribution that is claimed by the company. Now, they're not specifying like, oh, we think there's more orange or less red. They're just going to say that it's not the same. And it could be different, for one of the categories or several of the categories. Um, and if you think about it logically, if it's different for one of the categories, it's going to be different for the other one because if one's low, then one's going to be high, but I digress. Anyways, the point of that story is your hypotheses are going to be written in words, which I know we don't always love because wording is tricky, but I think the wording here is actually going to simplify things. Now, you could write them in symbols, but as you can see, I don't know that it's any simpler. Considering that you're not going to use these symbols later in your math, I don't know that it's worth writing them out in symbols. But hey, if you love a good subscript, then you go right ahead. Don't state the alternative hypothesis that suggests that all the proportions are wrong. It just says that something is different from what the original claim was. So how many candies of each color should we expect to find in our sample of 60 candies? Well, if all is on the up and up and those percentages are true, then out of the 60 candies, if we multiply them by the expected proportions, we're going to get this many red, yellow, and brown, and obviously same for green, and then a little more orange and blue because it had a higher percentage according to the company. So those are what we call our expected counts. And what we're going to do is we're going to compare what we observed to the expected count, and we're going to create this chi-square statistic in a moment. So the expected count for category and the subscript that uses I is just simply the number that you sampled times the proportion at which you think it should show up. We actually did this, oh gosh, back in chapter 6, I want to say. It might have been chapter 5, I forget. We were talking about probability distributions and expected values. We did a lot of this kind of work. Now, because the problems are going to be pretty simple in our problems, we're not going to, well, I guess we could use list one, list two, list three, all that good stuff, but we're probably going to just do them by hand. It's just as simple. So here they've displayed your data for each of the colors of the M&Ms, and they're comparing what we observed versus what we expected. And you'll notice that some of the categories are, the observed value was higher, some were lower, and nothing was exact. Some were close, but that's just the way the life works. So what we're going to try now is to figure out like how likely are these differences, just like how likely are they to occur just simply by random chance when we're sampling 60 M&Ms from the population. So was this a significant difference? Is it something to note? And we know that's the whole purpose of a hypothesis test. So the statistic that we're going to use to compare is called a chi-square test statistic. Chi looks like a weird squiggly X, by the way. It's a Greek letter. So you'll see it as chi-square. That's the symbol they're going to use. And this statistic is basically, it's measuring what they consider like a goodness of fit as a test. So some of your brains are thinking like, oh, like linear regression. And, it's in that family where we look at, how far are the observed away from the expected. And in linear regression, we call those residuals. So we'll kind of bring that notation back when we look in the rest of chapter 12. But for now, just look at that cute formula. So they're going to take the observed minus the expected counts. They're going to square those data values to make them positive. And also, now that we know more about stats, it's just to kind of make them more impactful, I guess would be a good word for it. So that difference is more obvious when we look at them individually. And then we're going to divide all those differences squared by the expected count to kind of find a ratio. And we're going to do that for each one of the categories, and we're going to add them up. So it's going to look like that for the problem of the M&Ms problem. So it wouldn't be terrible for us to do that by hand. I mean, it's not out of the realm of our capabilities. I will show you how you can use your calculator for help. And frankly, at the end of this, I'm going to show you how you can do the entire test on your calculator, although it's not recommended, simply because there's a high probability that you'll see a chi-square problem in the multiple choice test for the AP exam, and they like to set it up where like it's worked out but not actually calculated. So you have to understand how the calculation for chi-square is found. Alrighty, different question now. Carrie has a six-sided die, and it's rolled 90 times to test if all the sides are going to be equally likely to show up. Make sure it didn't get like weighted in some way. So this is her observed data in this chart, and we know if this is like a normal die that, each side should have a 1 in 6 chance of showing up. So what we're going to do is we're going to state our hypotheses. We're going to calculate the expected count for all the outcomes. That's going to be pretty easy. And then we're actually going to go and calculate the chi-square test statistic. So in words, which is much easier than symbols, the null hypothesis is that the sides of her die are equally likely to show up. And the alternative is that they are not. So literally all you have to do for the alternative hypotheses is just add the word not and make it like a two-sided test if you want to think of it that way. So our expected count, because it should be an equally likely event for each one of those sides, it's just going to be 1/6 of 90, which is 15. And it's going to be 15 for each one of the sides. So that wasn't too shabby. Now when we go to calculate the chi-square statistic, we take each one of those observed outcomes, subtract it from the expected outcome, square that difference to make it positive and make it bigger, basically, and then divide it by what we expected. So you'll notice all of them are being divided by 15. Blah, da, 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 da. They added them up and got 14.41. Now I know your brain is kicking in and you're thinking, oh, okay, 14.41, like what does that mean? We're going to talk about that in a minute. But for now you know how to find the chi-square statistic. So here is, I'm talking about the peanut chocolate candies. Favorite of mine. Unfortunately, in my house, we can't have them because my son is deathly allergic to peanuts. But they also give similar distributions from the company about what you'd expect to see for color. And then they took a random sample of 65 candies, and they have observed data there at the end of the problem. So they're going to want you to do the same thing they just did for that dice problem. You're going to state the hypotheses. Please use words, not symbols. That'd be better. You're going to calculate the expected count for each one of the colors. Now be careful. This time they're not going to all be the same. And then go ahead and calculate the chi-square test statistic for Joey's sample. So I want you to pause the video and try doing this one on your own because I'm about to show you a bunch of answers from the textbook. So the hypotheses in words is best. They just say the company's claimed color distribution for peanut M&Ms is correct, or the distribution of colors of the peanut M&Ms is what the company described. And then the alternative hypotheses is just that it's not. It's not the same as what they said. Now you could write those with subscripts and proportion sub blue, p sub orange, and so on and so on. But that seems like overkill. All right, so for part two, what they did is they found the expected values by taking the proportions and multiplying them by 65. So that's what you're seeing there. So for most of them, it was a 20% proportion was expected. So 65 times 20% is 13. And then the red and brown show up a little more frequent, or sorry, less frequently at 10%. So 65 times 10% is 6.5. So those are the expected values for the various colors for the peanut M&Ms. That's interesting. That breakdown seems, I wonder why. Weird. So anywho, the part three, now they're going to find the chi-square test statistic, and they're going to take the observed value minus the expected value, square that difference, and then divide by the expected value. And they're going to do it for each one of the categories, each one of the colors. We're going to add them up, and they get a chi-square value of 2.3846. Again, you're not really sure what that value means, and we'll come back to that in a moment. Like now. Okay, so we're going to use software to simulate taking 1,000 random samples of size 60 from a population distribution of regular M&Ms. So remember our original intro problem, we had the breakdown, we knew what we should expect, we found this chi-square statistic, but we weren't really sure what to do with that information. Like, okay, well, is that crazy? Should we have gotten that? So what we're going to do here is we're going to explore, before we talk about the actual chi-square distributions, we're going to explore some simulation data. So 1,000 of those random samples were simulated. And that is a really interesting looking distribution, right? So it does definitely seem to be, skewed to the right. And we'll see this note here says larger values of chi-square give more convincing evidence against the null and in favor of the alternative. So this distribution is kind of, petering off here to the right. It's skewed. And you'll see like the chi-square values, I forgot what we actually got on this problem. I'm sure they'll show it on the next slide, but you know, they're tailing off here, right around, I don't know, I'm kind of making up numbers, like 13, 14 for chi-squared values. So we're wondering like how likely are these events? Well, I think we have a p-value coming out in our future here. So the probability that that event happened just simply by random chance, or even something more extreme than that, is the definition of our p-value. So if we assume that that null hypothesis was true and we simulated a whole bunch of samples, they did 1,000 simulated samples, they did the count, and the observed value was okay, so 9.8 apparently was their observed statistic that Jerome found. I forgot already. Sorry, Jerome. So what they did then is they counted everything from like 9.8 and above. Well, 87 out of the 1,000 is how that happened. So the probability that that would just show up randomly or even more extreme is, 8.7%. So now you got to think about, what does that mean to you? That'll be the next part of our conclusion when we do a chi-square fitness, goodness of fit test. But I think you already probably have some ideas of how you feel about a p-value of 0.087. All right, back to this idea of a chi-square distribution. It is a density curve, and it's interesting though because it only takes non-negative values and it's always going to be skewed to the right. A particular chi-square distribution is defined by, oh, this is not new, a value called the degrees of freedom. Now, the degrees of freedom, you can see, will definitely change the look of the chi-square distribution. I mean, this greeny teal one is the higher degrees of freedom. I mean, I'm not going to claim that it's normally distributed, but it definitely changed the shape quite a bit as the degrees of freedom increased. It's still going to have this skew to the right, and then it only takes on non-negative data values. If you think about how that value was calculated, the fact that it's non-negative makes a lot of sense because remember it would at worst, I don't know, or best, however you want to think of it, be a zero because it takes the observed minus the expected and then squares it. Well, if observed and expected are the same, there's no difference, then you're going to have a zero there. So, yay math. As the degrees of freedom increase, the density curve becomes less skewed. The mean of a particular chi-square distribution is equal to its degrees of freedom. That's a very interesting idea, right? The mean is equal to the degrees of freedom. So you'll notice on this tealy one, the degrees of freedom were 8, and you'll kind of see where it's located on this curve. This red guy has a degrees of freedom of 4. Remember that skew is going to pull the mean, so that kind of makes sense visually where it's located. And then for degrees of freedom greater than 2, the mode of the chi-square density curve is at degrees of freedom minus 2. So the peak is going to be whatever the degrees of freedom are minus 2. Okay, that is a really interesting piece of information that I could see showing up on a multiple choice question. So I'm going to kind of tuck that away in my brain. For now, you don't need to worry about the whys and the hows, considering where we are in the school year. Sometimes it's just a matter of like having these weird random, knowledgeable things about distributions that might pop up on a multiple choice exam. I know it's crazy. All right, so back to that M&M problem. There were six color categories, right? So the degrees of freedom for that distribution is 6 minus 1, which is 5. And I know that's a different way of finding degrees of freedom. It has nothing to do with sample size. It has to do with the number of categories that we're using. So the p-value is the probability of getting a chi-square value as large or even larger um, than 9.8 when the null hypothesis is true. So remember, the p-value is the probability of just getting that value or more extreme than that value, just simply by random chance. So the idea is still the same. If the p is small, we're going to reject the null, because if there's a low probability of that occurring by chance, then that means that was a significant piece of evidence for us. So this is a display of that distribution we're talking about for the M&M problem. And you'll notice they marked off the value of interest, chi-square of 9.8. And um, they're going to go real old school, and they're going to show you what's called table C in our formula sheet. So for table C, if you're trying to find the p-value, the probability that you'll hit here or further, again, this is not table B, mind you, this is table C. It's going to be a chi-square value, and you'll see a little chi-square thing at the top of it. You go to the appropriate degrees of freedom. So for the M&M problem, that was 5. And then it's only going to give you an estimation because it's not going to be like, they can only put so many numbers on a chart, on a table. So when I look at 9.8 and you're going to look in your row of 5 and you're going to be like, oh, it's not there. Well, I know it's in between here, probably closer to the 0.10 than the 0.05. So all you can tell me right now is that the probability, the p-value of that occurring simply by chance is between 5 and 10%. Now, I'm going to show you technology next. You could use, instead of a normal distribution or a t-distribution, you could use a chi-square distribution. So chi-square distribution is going to ask you for your left bound, right bound, comma, degrees of freedom. So left bound value was that marker. It's always going to be that to something stupidly large and like larger than you would even think. I know a lot of people got used to putting like 100 or something down. Put something really stupidly large, like 99999, because chi-square do go a lot greater than your other distributions we've experienced because of the nature of that right skew. So turns out a more accurate answer for p-value calculation on the M&M problem is about 8%. Failing to reject the null hypothesis does not mean that we think it's true. It just means we don't have evidence to reject the null hypothesis. That's all. Oh, back to Carrie and her die. So remember, we found her chi-square statistic, to be 14.41. And now they want us to use good old table C to find the p-value, and then we're going to be a little more precise and use technology, and we're going to just assume all the conditions for inference are met, which we haven't really talked about that, and we really need to. It's coming up, I promise. So for Carrie, she had 6 sides to her die, so her degrees of freedom, 6 minus 1 is 5. If they went to table C, they would go down to degrees of freedom row 5 and try to find where 14.41 was. It was between these two values. When you look up top, they don't have a picture of the table here, I don't think. But let's be honest, guys, none of us are going to use table C. Like, it just seems like a waste when we have a calculator. So you could use your chi-square distribution, where you use a lower bound of the chi-square statistic that she just found, some stupidly large upper bound, and the degrees of freedom of 5. Notice if this was a free response question, they would need to see what you're doing, so you would have to write this out. And we're going to get a more accurate p-value of 1.3%. So this is an example, back to those peanut M&Ms. Oh, I love peanut M&Ms. And we're going to do a few things here. We're going to confirm that the expected counts are large enough to use a chi-square distribution to calculate the p-value. We're going to use table C to find the p-value. I feel like this problem is in the wrong spot. Yeah, I think it is. You know what? I'm going to come back to this problem. I got to fix this. All right. We haven't talked about this yet. We haven't talked about how you actually carry out the test. So, hey, it's our friends, the conditions. It's the same 3 conditions when we're sampling that we've been using for a while now. So the random condition means that you're taking random samples from a population of interest. 10% means that if you're sampling without replacement, you are selecting less than 10% of the whole population. And then this is a little different. Large counts has to do with all the expected counts, right? It has nothing to do with like how we did large counts before. So it's off of those expected counts we found, and each one of them has to be at least 5. So when checking the large counts condition, make sure to examine the expected counts and not the observed counts. Remember, this kind of goes back to the idea for hypothesis testing. You never want to use your conditions checking um, for the large counts condition with like the sampling proportion. It's always with the hypothesized proportion. So if you kind of want to relate your old idea to this new idea, it's always going to come back to the null hypothesis that the expected counts is what we're looking for in a null hypothesis to be true. Anywho, that's the same formula from before. This time now we know that the p-value is going to be the area to the right after the chi-square statistic, and the degrees of freedom are found by taking the number of categories and subtracting 1. All right, kiddos, it's time to do this. So this problem suggests that a hockey player's birth month has a big influence on his chance to make the highest level of the game. That's crazy. Oh well, let's do the math. Specifically, because January 1st is oh, this does kind of make sense. Okay, January 1st is the cutoff date for youth leagues in Canada, where a lot of them start. And if you were born in January, you'll be competing against like players who are almost like it could be up to a year older than you, or younger, I guess, younger. I can do math. The older players tend to be bigger, stronger, more coordinated, hence get more playing time, more coaching, have better chance of being successful. This sounds like a bunch of whiny parents to me. Make your kid play up if you're worried about it. Okay. To see if birth date is related to success, judged by whether a parent makes it into the player makes it to the NHL, a random sample of 80 NHL players from a recent season was selected and their birthdays were recorded. Okay. This is a table that summarizes the data from those 80 players. So here we go. Does this data provide convincing evidence that the birthdays of NHL players are not uniformly distributed across the 4 quarters of the year? So if everything was on the up and up, you would expect, each of the quarters to have 25% of the NHL players in it, right? So when we talk about setting up our test, we still start with stating our hypotheses. So the null hypothesis would be that they are uniformly distributed across the 4 quarters, meaning 25% of the players come from each of the quarters. Again, we wrote it in words, not symbols. I like that better. And then the alternative is that they are not uniformly distributed. You don't have to indicate anything beyond the fact that it's not uniformly distributed. And we're going to use a significance level of 5% because that feels good. So we are going to do a chi-square test for goodness of fit. The random condition was met because this was a random sample of NHL players. 10%. I don't really know much about hockey, but I'm pretty sure there's, more than 800 NHL players. But I've been wrong before. But remember, as we do these, we're assuming these conditions are going to come out yes. So let's just say yes, they are. And then for large counts, remember, we're working off the expected counts, not the observed data. So for each one of those quarters, you would expect to see a quarter of the 80 people from the sample. So you would expect to see 20 in each one of these birthday quarters. And 20 is obviously greater than 5. So check, check, check. So now they're calculating their chi-square statistic. They're taking each of the quarters, subtracting the expected 20, squaring that difference, and then dividing by 20. And they did that for all 4 quarters and added them up, and we got a chi-square statistic of 11.2. So now because we have 4 quarters, 4 categories they're falling into, the degrees of freedom is a 3. And probably nobody's going to use table C to find the p-value. Most of us will use technology. So if we use the chi-square distribution, that goes from 11.2 to something stupidly large with degrees of freedom of 3, we get, oh, interesting. Okay, I think I'm about to eat my words, guys. P-value is 1.1%. Interesting. So because the p-value is less than our significance level, we do reject the null hypothesis. See, what do I know? That's why you always got to run the data, Bruzo. We have convincing evidence that the birthdays of NHL players are not uniformly distributed across the 4 quarters of the year. Oh my gosh, that is something to think about. Now, my kids don't play hockey, so I guess I don't care. So now a little bit about carrying out a test, possibly using some technology. What they have here is that same NHL data. They put the observed value in list 1 of values, and then the expected in list 2. And then you can actually perform a goodness of fit chi-square test straight from your calculator. You just have to tell them where your observed and expected data is and what your degrees of freedom are. And then you can either choose calculate or draw. I'm going to go with calculate. The reason I like this, well, number one, we're towards the end of the class, and some of you guys are just looking to like get a point on a test, so I get it. It tells you everything you need to know. And if you chose draw, you would actually see a drawing of it, which is always nice. So here's the p-value, and then the chi-square and the degrees of freedom would be something I'd have to write down if I was using my calculator to do a free response question. And then here, these are called contributions. So if I go back and I think about how I found the chi-square by hand, each one of these values that would have been in my next list, if you want to think of it that way, where they took observed minus expected squared divided by expected, and then remember how we added them all up? Well, each one of these individual numbers before I added them up are called contributions. And the reason that's important is because the larger the number, the more swing it had to your chi-square statistic, if you want to think of it that way. So this first one here, this 7.2, remember that represented the first quarter of the birth year calendar. So like I think it was January to March. So there's a really big number here, which is creating a big portion of this chi-square statistic. That tells us, just kind of looking at the contributions, that that first quarter is really swinging the data. So when they say like all of these were the same, well, obviously not, and it looks like it's heavily loaded in the first quarter. Which goes back to my theory about weird parents. No, I don't think anybody out there is like timing their pregnancies like, oh, I really want my kid to play in the NHL. Let's make sure that my kid is born in January. No, I don't think that's part of it. I hope not. That's pretty weird. Okay, so when you run the chi-square test for goodness of fit on the 84 calculator, you're going to get those contributions. And they're also going to be stored in a list called contributions. So this actually goes back to the idea of residuals. Long time ago, we found out that when we ran a residual check on our calculator, the residuals were actually stored somewhere. I don't know if we tell you this right now, but I'll show you in class where we find that at. I actually like these contributions listed here when you do the test. And if for some reason this list is really, really long, you can just use your right arrow and scroll over until you can write them all down. Now, obviously, you could do all those by hand too. Okay, so a little tip about the test. You can use your calculator to carry out the mechanics of a significance test of any variety, but there is risk. So if all you do is give the calculator answer and no work, and if anything is wrong, you're going to get no credit. So I think for now, as we practice this, we do this by hand. And then we kind of use our calculator's test option to check to make sure we've done it right. Now, if it's multiple choice and you're feeling good, then go for it. Or, we talked about this before. Sometimes you're just running out of time, or maybe you're stuck on a question and you're like, well, I know it's chi-square. If you just jump into the do step because you have nothing else to work from at the moment, sometimes that gets like the thinking going. Like I often find myself doing that. It's not the greatest way to do a problem for inference, but if you're just staring at your paper like, oh my gosh, I don't know what to do, jump into the do step, see if you can get something that looks right, and then hopefully that'll trigger enough of your memory to say like, okay, oh, my reader's going to want to see all of this information now. Let's go back and kind of fill everything in. Again, not the best way to do it, but it's better than staring at your paper. All right, so the reason I wanted to do that first is now I'm going to go back to that silly question. I think I put this in the wrong spot. Boop, boop, boop. There we go. So back to those M&Ms. They're going to want us to confirm that the expected counts are large enough to use chi-square, and then degrees of freedom, find the p-value, interpret the p-value, and then what conclusions can we make? So we had that data from the M&Ms, the peanut M&Ms from an earlier check your understanding, and the expected counts, remember they calculated those before. These were all greater than 5, so that was the expected counts check. The degrees of freedom would be the categories minus 1, so 5. And then this is a picture of it. So yeah, the p-value, like I can tell from the picture, it's going to be really high, right? The p-value is almost 80%. So this is the interpretation of the p-value. Ready? Assuming that the claimed color distribution for peanut M&Ms is correct, so that's us assuming the null hypothesis is correct, there's an almost 80% probability of getting that value or larger just simply by chance. So that means we failed to reject the null hypothesis. We do not have evidence that the color distribution is anything different than what the company claims. So good job, Mars. You're not lying to us. I would like to meet the person who cares this much about the color of M&Ms. I swear we just do this example because it's easy for us to look at and everyone likes M&Ms. Now, this hockey player example really fascinates me. I would like to look more into this. Again, my kids don't play hockey, so I don't really care, but I thought that's pretty interesting. Oops, back up. So now we're going to do some follow-up analysis. We talked about looking at those contributions and like what we can gather from those data values. So if the sample data leads to statistically significant result, we can conclude that our variable has a distribution different than the one stated. How the distribution is different, you want to look at the contributions. So this was that hockey example. And when we look at this last column here, this is them finding each of the what they call the contributions. We pointed out that this January to March one was like, that was the one that really messed with the data, right? So April to June was not off at all, slightly higher in July to September, and then quite a bit in October to December. This is probably all those weird parents who are trying to have a baby in January and the baby came early, right? I'm kidding, guys. No one does that. All right. So the two biggest contributions to that chi-square statistic came from January to March and October to December. So in October through December, eight fewer. Oh, yeah. So that was my bad. It was negative. I didn't look closely. Eight fewer players were born than expected. And then that kind of goes hand in hand with the idea that 12 more were born than expected in January to March. Because for the data to work out, like if you have an overage on one category, you're going to have an underage on the other category, if that makes any sense. All right. Does warm, sunny weather in Arizona affect a driver's choice of car color? Cass thinks that Arizona drivers might opt for a lighter color with the hope that it will reflect some of the heat from the sun. To see if the distribution of car colors in Oro Valley near Tucson is different from the distribution of car colors across North America, she selects a random sample of 300 cars in Oro Valley. The table shows the distribution of car color for Cass for her sample, and the distribution of car color in North America according to some website that actually keeps track of this. So what we have here is our sample data out of 300. And then this is the expected counts. I shouldn't say the counts. This is the expected ratio that we would expect them to be in. So they want to know, do the data provide convincing evidence that the distribution, so basically they want you to perform a chi-square test. So we're going to have to fiddle with this data a little bit because you want to talk about, counts and not necessarily what they have here. For the null and alternative hypothesis, I always prefer you guys to write these in words, but the null hypothesis is just that the distribution is the same as everywhere else in North America. So as far as the colors of the cars. And then the alternative hypothesis is that it is not the same. So literally, you just have to add the word not. That's why I prefer the words. If you prefer subscripts and symbols, you go for it. We're going to use a 5% significance level. So we are going to do a chi-square test for goodness of fit. That's the official name. The data was selected as a random sample of 300 cars in Oro Valley. The 10% condition, I'm sure 300 is less than 10% of all cars in Oro Valley. Large counts. Now, this is the part I'm worried about. Remember, it's not the observed data. It goes back to your expected values. So if we selected 300 cars in our sample, we expected 23% to be white, and that came from the North American data. So we should have seen 69 white, 54 black, 48 gray, 45 silver, 30, what are we, red, 27 blue, and so on and so on. So they found that value by taking the sample size but multiplying it by what we expected as a percent. Remember, that comes from the null hypothesis. So then they calculate the chi-square statistic by taking your observed minus your expected, squaring it, and then dividing by the expected. And they found each one of these and added them up, and you got 29.921. Now this was us doing it by hand. We're going to continue doing it by hand. For the distribution we're looking at, the degrees of freedom was 7. And then to find the probability that you would get a 29.921 or higher is really stinking small. Point less, oh my gosh, like almost 0. Using technology, it's even more extreme. And this was using table C, by the way. So using technology, it's even worse. It's literally almost 0. So because that p-value is so small, much smaller than 5% for alpha, we are going to reject the null hypothesis. We have convincing evidence that the distribution of car colors in Oro Valley is not the same as the distribution of car color across North America. All right, good deal. Now, this table specifies something that we're going to need to answer the second part of the question. And if you remember, the second part of the question says if there is convincing evidence of a difference, perform a follow-up analysis. So let's look at the contributions that each one of these colors gave us. So as I look through the values, like other is a pretty high contribution, and it's in the positive direction. White, it was positive, O minus E, and pretty big. And then you'll notice black and gray are pretty big contributions, but in the negative direction. So the two biggest contributions from the chi-square statistic came from gray and other colored cars. There were fewer gray cars than expected and more of these, quote, other colored cars. And you wonder what these other colors are, right? It does seem that drivers in Oro Valley prefer lighter colored cars as there were more white cars than expected and fewer black cars. So I feel like, she's onto something. However, and I'm going to say an unpopular opinion right now, guys, I don't know anything about Oro Valley, but I know that a lot of the communities in what state was this in? Arizona. Yes, a lot of the communities in Arizona are heavily populated by retirees and older individuals. I don't know if you've noticed this, but in my observations, older individuals tend to use lighter colored cars. I don't know if I'm onto anything there. Maybe Cass and I should team up and figure out if we could look at the age demographics as well. All right, that's your introduction to chi-square statistics. I feel like someone told me that we do these in our AP Bio class if you've taken that. We'll have to take a look at that and see if there's some fun projects we can get together with AP Bio and in the future. All right, good luck, everybody.